Hi, in this lecture, you will learn how to perform a modular inversion by using the extended GCD algorithm. So assume that you have the following question. Let's invert 391 modulo 792. Now, how is this relevant to cryptography? Well, in the RSA function, right, you have that E times, so E, the public exponent, times D, the private exponent, is congruent to 1 mod phi of n, okay? So we need to solve, when we were given the public exponent and phi of n, we need to find D in order to have the right parameters to execute the RSA function in both directions, okay? So in this particular example, so what we're using here is the extended GCD algorithm. So what does this mean? We want to find x and y such that x times 792 plus y times 391 equals d, which is the GCD between 792 and 391. Okay? Now, and we hope, of course, that that GCD is going to be 1. Okay. Now, the extended GCD algorithm will calculate x and y and d all at the same time. But for this inversion here that we're seeking to exist, there has to be that the both numbers are coprime. Okay. So, we're expecting here, for this question to make sense, we're expecting that d is going to be 1. But the extended GCD is going to confirm that for us, okay? So how does this work? So now we're going to focus on this task, and we're going to see at the end, well, we can see it right away, that once we have that, then our inverse of 391 is going to be the number y, okay? We'll circle back to that once we're done with this task of finding x and y. Okay, so how does the extended GCD proceed? Well, we calculate a sequence of xi's, yi's, and ri's, okay, where at each step, we always have the relation xi times 792 plus yi times 391 equals ri. And of course, once we get to ri equals 1, or, in this case, or theoretically, we don't know what it's going to be 1, then if we get to Ri is D, the GCD, then we win, okay? And so the Ri's are calculated with the standard Euclidean algorithm by subsequent divisions, okay, of Ri minus 1 by Ri to produce Ri plus 1. Okay, so if you have 2 Ri's, so you get the third one. So now we have to initiate that sequence. So how do we initiate it? Well, we initiate it with the trivial relations that if we take R0 to be 792, right? How do I find an x0 and a y0? Well, it's pretty clear that if I take x0 equals 1 and y0 equals 0, I will have 1 times 792 plus 0 times 391 equals R0, which is 792, right? And now, just as arbitrarily, I need to, not arbitrarily, but I need to initiate now the second term, okay, to be able to start an induction where each pair of consecutive term gives me the third one. So R1 is going to be 391. And now how do I get that x1 times 792 plus y1 times 391 equals R1? Well, simply by setting x0 equals 0 and y1 equals 1. So that's for the easy steps, okay? Now, to get to R2, remember R2 is going to be the remainder of the division of R0 by R1, okay? So what do we have here? We have that R0 equals, so 792 equals 2 times R1 plus 10, okay? So here R2 is 10, okay, because 792 plus 2 times 391 plus 10, I mean, equals 10, right? So now to find an x2 and a y2, what we need to do is first rewrite R2 as a linear combination of R0 and R1, okay? All right, and now remember, I know how to express R0 as a linear combination of 792 and 391, and same for R1, okay? So by linearity, I'm going to be able to write down R2 as an x2 times 792 plus an y2 times 391. And so that process is pretty straightforward, but I'm gonna explain all the steps here. So R0, let's rewrite it. So we know it's x0 times 792 plus y0 times 391. Okay, fine. And now we have this is probably, I want to be careful here. I'm running out of space. So I'm going to go minus 2 times x1 times 792 plus y1 times 391. All right, and now by linearity, I can regroup the terms. What do I get? I get x0 minus 2x1 times 792 plus y0 minus 2y1, and apologies, I'm running out of space, times 391. All right. And so if I squeeze just a little bit, and so this is my x2, okay? And it turns out that it equals 1, okay, because x0 is 1 and x1 is 0. And this is minus 2, okay, because y0 is 0 and y1 is 1. So y2 equals minus 2. All right. So now I have my R2, which is 10, my x2, which is 1, and my y2, which is minus 2. And I'm ready to proceed on to the next step, okay? So now I need to, so I'll remember, that's not ideal here. Let me see. So we'll have to remember here that x1 equals 0 and y1 equals 1. Okay, that's all we need to remember at each step, okay? So let's just remember that. And now what we have is we divide R1 by R0. So R1, which is 391, it breaks down as, in the integer division, as 39 times 10 plus 1, okay? And this is R3, okay? So R1 is a quotient times R2 plus the remainder R3. Okay, and now what do I have for R3? So I can rewrite R3 as R1 minus 39 times R2, okay? And remember, what I want now is X3 and Y3, okay? And so what do? I rewrite R1 and R2 with respect to 391 and 792. So, and by linearity, I'm gonna get my result. So that's gonna be X1 times 792. And I'll do all the steps here. So plus y1 times 391 minus 39 times x2 times 792 plus y2 times 391. Apologies for going a little over. All right. And now I can regroup the terms in 792 and those in 391, okay, to find x3 and y3. So, so that gives me x1 minus 39 times x2 times 792 plus y1 minus 39 39y2, sorry, times 391. All right. And so now I need to calculate that x3. This here is going to be x3, and this here is going to be y3, okay? So how do I calculate these values? I remember that I'll have x1 and x2, okay? So here I have that this thing is minus 39, okay? Because x1 is 0, x2 is 1. And this is 79 here, all right? So what I have now is x3 is minus 39 and y3 equals 79. And since r3 was equal to 1, I have that minus 39 times 792 plus 79 times 391 equals 1. Now, I have my inverse, because what I can do now is say, from this, I can regroup the term here in 391 on one side of the equality, and that's plus 39 times 792, and obviously this is congruent to 1 mod 792. So the inverse, so n inverse, because I did not specify, inverses of course are not unique, right? They're all the classes, and their entire congruence class of 79, but in particular an inverse of 391 modulo 792 is 79. That is my inverse, all right? So now you know how to calculate a modular inverse using the extended GCD algorithm. Thank you very much.